Well, hello everyone. A very good morning, good afternoon, and good evening to all of you. It's depending on from where you are watching this event. I know many of you are watching outside of India also, and not only in Bengal but other parts of India also. On behalf of Jhargram Raj College, Physics Alumni Association, and the Department of Physics, Jhargram Raj College, I welcome you all in our YouTube channel. Today we came with another exciting webinar for all of you. This is our third initiative, and the title of today's webinar is An Overview of Experimental Physics and its Application. I believe we all able to learn some facts about some exciting science experiments today from our speakers. Personally, I am also excited about today's talk as I had a divorce to physics almost 12 years back. However, due to this coronavirus spreading situation, people are scared. No one know what to do, and no one know when is the end point of this. However, scientists continue to do practice science. One such example is Isaac Newton. It is said that he started his work on gravitation while he was in quarantine during the period of the Great Plague in Britain in 1966 and 67 year. However, we don't know whether the apple fall on his head or not, but the message from me is that please be safe, take all precautions, whatever you can do, but do your education, research, and other job. Otherwise, if you continuously think about some stupid virus, then you may lose your immune power, and it will be very dangerous for you in this time. On that respect, we organize a series of webinars from our association jointly with Department of Physics. Now, to start this event formally, first I want to request the principal of Jhargram Raj College, Dr. Dept Roy, to formally open today's session. Dr. Roy, please.
Good afternoon, everybody. Respected Dr. Chandrakanta Kumar, Senior Scientist of Indian Space Research Organization, Dr. Sailajananda Bhattacharya, former Head, Physics Department, and Ex-DAE Ramanna Fellow, Variable Energy Cyclotron Center, Kolkata, other dignitaries, academic luminaries, esteemed colleagues from different institutions, my dear students, ladies and gentlemen. On behalf of the Office of the Principal, Teachers Council, Internal Quality Assurance Cell, non-teaching staff, Student Council, and also on my personal behalf, I heartily welcome you in Jhargram Raj College. The Jhargram Raj College started its journey as Jhargram Agricultural College in 1949. And it was truly a brainchild of Sri Narasingha Malladev Raj Bahadur, the 16th ruler of Jhargram royal family. The college was established on 327 acres of land and received lavish patronage from the royal family of Jhargram. The government of West Bengal took over the college in 1953 and was affiliated to University of Calcutta. The college is now affiliated to the Vidyasagar University since 1985. The college celebrated its golden jubilee on 8th May 1999. Jhargram Raj College was the only government college of undivided Paschim Mednipur district. And now there are 17 new government colleges are established in Jangal Mahal area. And we are proud to share you the fact that we had been mentoring all the newly established government colleges until they stand on their own feet. Presently, Jhargram Raj College is one of the most prestigious government college of the district. Jhargram engages in educating the first generation learner from the socially and economically backward community and from the tribal families. There are a total of 15 departments in various science, humanities, and commerce discipline, the Department of Chemistry, Zoology, and Bengali offer postgraduate degrees since 2005. There are also two boys' hostel and one separate girls' hostel, making our college a partially residential campus. The college as a whole caters more than 3,000 students. A large number of UG students are able to secure first class in the university examination, and quite a few number of students qualify JAM and other national level competitive examination to pursue MSc degree in various national institutes of repute in every year. Almost 90 to 95% of the postgraduate students score first class marks in their qualifying examination, and many of them qualify NET, SET, etc. for research fellowship and lecturership. In the year 2019, our college came under prestigious DBT Stars College scheme offered by Department of Biotechnology, Government of India. Very recently, we achieved the Educational Excellence Award conferred by G24 Ghanta. Recently, we get an honor to extend more than 4,000 online courses to 3,000 enrolled participants through Coursera Organization of United States of America at free of cost with pass out certificate. The diversity of scientific opportunities that now exist in Jhargram Raj College has grown out of a long and distinguished tradition of physics teaching and research. Jhargram Raj College graduates, along with many other successful persons who spent their formative years here, have gone on to make extraordinary contribution to the science as scientists, researchers, teachers, and intellectual leaders all over the country as well as on international platforms. The Jhargram Raj College Physics Alumni Association was one of the reputed alumni association was started its journey on 18th December 2015. The aims of the association shall be the enhancement of educational, social, and cultural development through lectures, symposia, conventions, workshops, literature, cultural program, different kinds of communities, services, and awareness camp, exchange programs for the alumni and the students of Department of Physics, Jhargram Raj College, and others. Our physics department marked as one of the best departments in the state. It is a great historical moment for me that our Jhargram Raj College Physics Alumni Association and Department of Physics, Jhargram Raj College, is going to organize an exciting and resourceful webinar on an overview of experimental physics and its application for the benefit of the teachers and students of all over the country. This is the 10th webinar program of our college, and this is the third initiative of Jhargram Physics Alumni Association of this year. We hope this webinar is very much pertinent to present situation. Actually, we do not know after how many days we will be able to overcome the present pandemic situation of COVID. We also do not know after how many days the normalcy begin in our society. I hope the deliberation of our honorable speakers, Dr. Chandrakanta Kumar, scientist, senior scientist of Indian Space Research Organization, and Dr. Sailajananda Bhattacharya, former head, Physics Department and ex-DAE Ramanna Fellow, Variable Energy Cyclotron Center, Kolkata, is not only enrich our knowledge, but also boost up the mental strength of our participants. With this, I once again express my heartfelt gratitude to all honorable speakers for sparing their invaluable time with us. I wish a grand success of the program. With these few words, I formally open this program as open and declare open this program. Once again, I express all of you my heartiest gratitude to you. সবশেষে আপনাদেরকে আরেকবার কলেজের পক্ষ থেকে শিক্ষক সংসদ পদার্থবিদ্যা বিভাগ আমাদের ঝাড়গ্রাম রাজ কলেজ অ্যালামনি অ্যাসোসিয়েশনের পক্ষ থেকে আন্তরিক শ্রদ্ধা, যথাযোগ্য স্থানে আমার প্রণাম, প্রীতি, শুভেচ্ছা, ভালোবাসা। আপনারা ভালো থাকুন, সুস্থ থাকুন। আমাদের অনুষ্ঠান আশা করি আপনাদের ভালো লাগবে এবং আজকের অনুষ্ঠানের সর্বাঙ্গীন সাফল্য কামনা করে আরেকবার আন্তরিক শ্রদ্ধা অভিনন্দন জানিয়ে আমাদের আজকের অনুষ্ঠানের প্রোগ্রাম কোঅর্ডিনেটর, মে আই রিকোয়েস্ট প্রোগ্রাম কোঅর্ডিনেটর Dr. Minal Kanti Hota to proceed the next session of the program. Our best and very best wishes to all of you. Thank you. Namaskar. Dhanyawad.
Thank you, Dr. Rai, for your encouraging remarks. And also, it is nice to see that you explained very well the present activities of Jhargram Raj College during this pandemic situation. I think it will be very useful for the students, particularly. Now, let me ask convener of this webinar series, Dr. Sandeepan Mallik, to formally welcome all of the guests and all the viewers, everybody. Dr. Mallik, please.
Thank you, Dr. Minal. A very good afternoon to all of you. I'm delighted to inform you that the Jhargram Raj College Physics Alumni Association and Department of Physics, Jhargram Raj College are jointly organizing a series of webinars on different technical as well as non-technical topics. And today, 12 September 2020, we are going to organize the third webinar entitled Overview of Experimental Physics and its Applications. The first talk entitled Linking Space Mission and Few Basic Concepts of Physics will be lectured by Dr. Chandrakanta Kumar, Senior Scientist of Indian Space Research Organization. The talk will be held from 2:30 p.m. to 3:30 p.m. The second talk entitled Experiments in Science Triggering the Charge will be lectured by Dr. Sailajananda Bhattacharya, former head of the Department of Physics and Ex-DAE Ramanna Fellow, Variable Energy Center, Cyclotron Center, Kolkata. The talk will be held from 3:30 p.m. to 4:30 p.m. Experimental physics is the category of disciplines and sub-disciplines in the field of physics that are concerned with the observation of physical phenomena and experiments. Experimental physics regroups all the disciplines of physics and that are concerned with the data acquisition methods and the detailed conceptualization and realization of laboratory experiments. Although experimental and theoretical physics are concerned with different aspects of nature, they both share the same goal of understanding it and have a symbiotic relation. The former provides data about the universe, which can be analyzed in order to be understood, while the latter provides explanation of the data and thus offers insight on how to better acquire data and how to set up the experiments. In today's webinar, our esteemed speakers will enlighten you by briefing out an overview of experimental physics and its application in their corresponding domain. Participants are free to post their questions in the chat box of YouTube live event or can post in the message box of official website of JRCPAA. Please do not forget to mention your mail and email ID. Your name and email ID when you are posting your questions. We will try our best to answer those questions later by communicating with you. E-participation certificates will be provided to the registered candidates within next 7 days. I heartily welcome Dr. Kumar and Professor Bhattacharya, and I would like to express my sincere gratitude and deep appreciation to them for giving us their precious time. I welcome on the participants of this program. I would like to thank Principal of Jhargram Raj College, Head of the Department of Physics, our present and ex-faculty members of Jhargram Raj College, the webinar organizing committee members of JRCPAA, advisory committee members, secretary, president, and all other executive committee members of JRCPAA for their kind support throughout to make this program success. At the end, it is our sincere request to you to subscribe our official JRCPAA YouTube channel to get the notification regarding our upcoming events. Please stay tuned and enjoy the program up to end. I request Dr. Minal to take on the program into the next part. Thank you very much to all of you.
Well, thank you, Dr. Mallik, for your opening remarks. Now, before I move to the first speaker, let me ask one question to the viewer. How many cases do you know where the person's name match correctly with his job? When a child born, parents give the name of their child as per their choice, but parents don't know what will be the destination of that baby. But this is exactly happened to our very first speaker, who became famous last year due to one of his activity, and that is directly matched with his name. That is very, very good coincidence. To introduce that speaker to all of you, I believe we need another very famous person. He is very famous in Jhargram, particularly Jhargram Raj College and surrounding area. He is very active in his retired age also. He is our beloved Professor Ranjan Chaki. I know him personally as an artist of creating career. So I want to request Professor Chaki, please introduce our first speaker today. Then our first speaker will start his session. Sir, Professor Ranjan Chaki, sir, can you hear me? Hello? Hello, sir, can you hear me? Ranjan Chaki, sir, can you hear me? I can see his video, but I don't know, something happened to it in his end maybe.
Mic ta unmute করতে হবে।
Sir, your mic is unmuted already.
আচ্ছা স্যার, আপনাকে মানে আপনার স্টকটা দেওয়ার জন্য বলছে মৃণাল আর কি, আপনি মনে হয় শুনতে পাচ্ছেন না? ওকে। ও না, শোনা যাচ্ছে না স্যার। না স্যার, আরেকবার জয়েন করেন। Is coming.
What happened?
Some problem with his mic. Is rejoining again. Just 2 minutes.
Oh, well, okay, no problem. So we can wait maybe 1 minute more. I think Sir is facing some problem, most likely. So in this condition, I think it's my privilege to move on. So what I can say, anyway, this okay. Anyway, so I think Anjagi is not able to come now. So let me introduce the speaker to you all again, because many of you, if you follow the news, then you may know Dr. Chandrakanta Kumar, his name. Last year, he became famous due to the Indian ISRO's space mission Chandrayaan-2. Presently, he is the head of electromagnetic section of URRAO Satellite Center. But Dr. Kumar is from a very remote village. He is born in Shivpur, West Bengal, India. He received his both MTech and PhD degree in radio physics and electronics from University of Kolkata in the year of 2001 and 2012 respectively. He has completed his space studies program from International Space Universities, France, 2013. After that, he's joined ISRO in 2001 as an engineer. He primarily designed and developed the antenna systems for the Indian space program and related ground station. He has more than 50 international publications in the peer-reviewed journal, and he supervised 2 masters and 2 PhD theses. And not only that, he was associate as a project manager in the antenna system for Chandrayaan-1 mission, GSAT-12 mission, and also he served as a deputy project director for the RF system of Chandrayaan-2 orbiter. Dr. Kumar is now actively as a volunteer of IEEE and he is the president and joint secretary of the Bangalore section. Today, Dr. Kumar will give his talk on the topic of linking space mission and few basic concepts or physics. Now, without not wasting much time, I want to request Dr. Kumar to please start your session.
Thank you, Dr. Meena. Am I audible? And my
Yeah, you are audible. You are audible, loud and clear. Please.
Yeah, thank you. So to start with, I thank the Raj College, Jhargram Raj College management for inviting me, and as well as the Alumni Association. It's a privilege to be part of this talk. And when Professor Chaki told me that you have to give a talk, he requested me. Then I was just wondering what to talk. So then Dr. Mrinal came into picture. Then I, in consultation with him, and whatever came to my mind, I thought I'll talk on this as topic, and I gave to him. And then it evolved over the time, and so now the title of the talk, what I could finally put is like this: on some basic concepts of physics and space mission. So before starting the talk, I must thank the principal of Jhargram Raj College and HOD of the physics department for their support and encouraging word. From the words of the principal, I am feeling tempted to see Jhargram Raj College, because 300-acre campus, it's really wonderful. I can believe that one. So it should be beautiful in the lap of the nature. So to start the thing, let me start with the first slide itself. You can see the nice, and after picking up the topic, then I understood that I have to sell a refrigerator to Eskimos. Initially, I thought, okay, I'll talk something about physics, this, that, but then I realized when preparing that, okay, everybody is a physics teacher, so I have to sell a refrigerator to Eskimos. So that is the job I have taken on my this one. Because I believe my work of field of work is very narrow, and it's very difficult to convey to this one. So, and that's why I have confined those my work area of work into last 2 slides only. The last couple of slides will be on that. So whatever you have heard about me, just forget about all these things, because I may not be worthy of those things. So let me just put across my thoughts on the topic what I have tried to discuss with you. So you can see a nice picture here, and that is the picture what we see in the full moon day, the moon in the background of nice stars and all these things. Now, if you do the, if you see from moon how we look, how our home looks, this is how we look. So once it was asked to astronauts that when you leave the Earth, means when it's mission, what do you feel? He told, first thing what comes to our mind is we become a philosopher. Means that time you understand that what is this world all about. Now, if I go to a little further, means this was the nearest celestial neighbor from our Mother Earth. Now, if I go to the next one, that is on the Mars. If I take our picture of our home from Mars, it's like this. Are you able to point anything here? So that is us. Where the cursor is, that is us. So this is how big we are. This is how big we are from our nearest neighbor, that is Mars. So within this, we are maybe 100 billions of living creatures, and our all knowledge, our all egos, everything is concentrated in this small dot. So if you enlarge this part, you can see this is our Earth and this is our moon. It is all concentrated in a small dot. So that's how big we are. So that's how makes me feel humble when I see this picture again and again. I took this picture from Dr. Gautam Chattopadhyay. And sometimes we say that we are in a space mission. That means we are going to space or something like that. So this picture actually gives you a feeling that we are indeed in space already. It is not that we are going to space. And Earth is nothing but a cradle of humanity, and mankind cannot stay in the cradle forever. With this small introduction of myself, I just slip into my thought. Hope I'm audible, everybody. So the agenda, whatever I thought of sharing with you, that I just wanted to connect the basic science with our space mission. I felt that when I also was I am a student of physics. Even today, I am learning every day. So when we started learning the physics, there we used to feel that there may be some disconnect with respect to the concept of the physics and actual application. So with that thought, we started. Then we'll just see how we can leave Earth and reach another celestial object, and need of such mission, challenges, and if you want to have a manned mission, what are the other challenges you have to face. And in this process of challenges and constraints, and this provide the opportunities for the engineers and scientists to innovate in their design and implementation. That is all about my talk. So if I start with a simple concept that on Earth, you go to a high-rise building, say, and you carry some of the stones with you, and you just throw horizontally some of the stones. So if you use some force, so it will reach some distance, maybe this one. If you apply some more force or some faster, if you can throw, it will reach some further distance. And depending on the energy that you impart, stones will go. But after some time, you can imagine, because Earth is a spherical object, so after some time, you can imagine that the stone, it may miss the Earth like this. It may miss the Earth. Then it will be always falling. Means it will not be able to touch the surface of the Earth, and it will be always falling. And if you throw even further, with further energy, then it will go even further away from the Earth's surface in this direction. So what happens? Now, when you are imparting just enough energy, then you are just missing the Earth. So this will be the way you will be following the Earth. This is the point of your release, and you'll be following the Earth like this. And in ideal condition, you're supposed to be in this orbit only, but because of some imperfection and all, this orbit will gradually decay, and you'll be landing on the surface of the Earth after some time. Now, if you impart a velocity, it is that is dictated by this. G is the universal gravitational constant, m is the mass of Earth, and r is the distance of, means from the center of the Earth to the tower. So equal to this energy, then you'll be having a circular orbit, this orbit. That is the circular orbit, the minimum energy orbit that you can have with a velocity of this. You can see, if you increase the height, that means if you go further above the sky, if you go above and high above, then your velocity requirements comes down. Because you can imagine when you are throwing the stone in horizontal direction, it is falling downwards with a gravitational pull, and it is moving forward with the velocity whatever you have imparted. So as you go up, so it takes more time to fall. So you can to travel the same distance, you have more time, so you can go a little slower. Now, if you increase the energy to a value that is called a step energy, that is given by Gmm by r square, just exactly to this value, then your orbit will no longer be a closed orbit. Then you take a parabolic orbit. Parabolic orbit means it doesn't come back again into its place, so it will be open orbit. And if your energy increases even further, that orbit becomes hyperbolic, and you leave Earth. So this is how you can leave Earth. Now, when you leave Earth in the quest of reaching another object, so you have to hold your attitude. Means when you are trying to study something, so you cannot lose your focus. So in that process, the basic conservation of angular momentum and conservation of linear momentum. Those two concept drives the next part of the mission, that is from the release of the object to reaching the other part. Now, that is the linear momentum of the thing will be conserved and angular momentum of the object will be conserved. Just if you want to reach one destination, it is not always correct that you will be always in the same path or the correct path. There may be some dispersion in the in between happening. So you have to correct this. So how to change these things? Unless you change your linear momentum and angular momentum, you cannot change your direction or change your path. So here I have put a picture of some nice balloons. They are just flying high and freely. Now what happens if you just untie one of this balloon here in the, or you can puncture one of the balloon? What happens? The gas inside the balloon, it's come out through the nozzle or through that leakage addition hole, and it starts moving. The balloon starts flying opposite direction. So same principle is used. So your object or your satellite or whatever it is having an engine. So it starts burning that fuel and it ejects some gas and backwards, and its forward direction energy changes. So that's how, using the property of conservation of linear momentum, you can increase the velocity of your vehicle or object. Or if you orient the the thruster, this is called thruster, in a reverse direction, then your velocity can be reduced. So like this, you can change the velocity of the object. And to change the angular momentum, another parameter that you have to change the orientation. This is the concept, very simple concept. When the tops are not rotating, they will be lying down the way it is given here. But when it is spinning, it is very steady. That is nothing but your angular momentum is conserved. If you try to disturb this one, it will come back to its own place. So this is the way we try to hold the attitude of the object or the satellite in our spacecraft. So we put 3 such tops rather, in the name, in the technical flywheels in X, Y, and Z axis, and we rotate with a good speed such that they are stabilized and our full object is stabilized. And in actual condition, we use 4 of them, not in an orthogonal condition, in a tetrahedral condition. Because in orthogonal condition, if you have a x-axis one flywheel, so it will not have any component in y and z axis because they are orthogonal. So if you want to change the orientation of the spacecraft, it is not possible. So you have with some angle such that any of the angular momentum, if we change the velocity of the wheel with the electronic drive, so that has a reaction to the other axis, and you can change the orientation of the spacecraft. And in actual spacecraft, the 4 wheels are mounted in this condition. You can see inside the wheels, and it has a drive, electronic drive. If you deliver more current, its speed will increase, and if you deliver less current, its speed will reduces. So accordingly, its orientation you can change. So in the object, whatever is flying, it's in an orbit, whatever is supposed to be free. So you can change this way the orientation and the velocity of the object to reach the final target. And this is how a typical mission profile looks like. So initially, the this launcher, your whatever launcher you have, it will be launching the orbit into a elliptical orbit of a smaller dimension. Then every time this object comes to this perigee, so there this sort of engines, that is gas engines, will be ignited. So some thrust will be imparted, and more and more energy you give, the size of the orbit increases. You can see it increases. So its apogee height increases. Now, if you have to reach to a different planet or different object like moon, so the day you are launching your spacecraft, the moon will be somewhere other place. So you will be reaching to that place, the moon or Mars or whatever object it is. So in that time, you have to plan your strategy like such a way that in that time. So it takes some 10 days or 15 days for you to reach there. So your moon or that object should be in that particular, close to that orbit. Now, when your object comes close to the targeted object, so there the gravitational field of this targeted object starts interacting or start pulling it towards it. But what happens if you have enough energy? You can just miss its gravitational pull. So you have to reduce your velocity when you are under the influence of the target object, that is moon or Mars. So you just reorient your thruster in the opposite direction of the velocity and again fire it. So velocity, instead of increasing, it will reduce. And if you reduce the velocity, the moon's gravity or the gravity of the Mars will capture the spacecraft, and then you'll be having a orbit, which is the biggest orbit you'll be having. And just you do the reverse maneuver, whatever you did around Earth, that is firing the engine in opposite direction of the velocity vector, then your size of the orbit will be reducing, and ultimately it will be coming down to a lower size orbit, maybe 100 by 100 or something like that. Still, your velocity will be able to maintain you in the orbit. Now, if you want to come down on the surface of the Earth, so you have to see that velocity equation. That is, you have to reduce the velocity below the orbital velocity. So again, you reduce your how to reduce the velocity. Again, fire the thruster in the reverse direction. So your velocity will be reduced from the orbital velocity. So you will start falling down, and there will be a controlled. If you can keep this spacecraft under control, that is using the control system and thruster firing, all these things, then you can slowly come down and have a smooth touchdown on the surface of the celestial object, whatever you are using. But it is very difficult job. It is not, you can imagine, say, if you are having a moon mission or something like that, your distance involved is close to 4 lakh kilometers, and at the end, say last in maybe 5-10 kilometers, you have to estimate the distance within meters accuracy. Can you imagine a 4 lakh kilometer distance has, at a distance, the object has to estimate the distance with the accuracy of 4 lakh kilometers, sorry, in meters. So that is the challenge that we have, but the basic physics remains the same. So how to implement that one, that is a different job. And that's how you can reach another planet. And because in the most of the planet there is no atmosphere, so there is no most of the cases there is no help of parachute or anything like that. So it has to be most of the time we have to depend on the thrusters. Now, how in the process of reaching there, how will you reach? See, if you have to reach a certain place in Kolkata or Jhargram or Bangalore, nowadays we can use the GPS, but just think over it that beyond some distance, maybe 2 lakh kilometers maximum, as of now, there is no GPS signal available. So how to navigate it? So for the navigation, we use a very interesting concept. It is nothing but the Doppler. Doppler we have always studied in our colleges, even schools also we have studied, and we have done so much maths, but we have seen that whistle blowing of a train, that is the maximum practical thing that we have come across about the Doppler. Now to navigate the spacecraft, so you first know where the spacecraft is. So to do that, you have to derive this information from the spacecraft. Then you need to know where it was supposed to be, such that you can think that, okay, this is the error that has come. So for that, you need to have a computation or simulation available with you. And how to correct it? Correction is nothing but implementation of thrust, reduction of the velocity, increase in the velocity, change in the orientation, include using those wheels or some thrusters. These are the things you have to have. Now to know where is the spacecraft, what is the means? It is a very simple concept. Just send a carrier. Carrier means like a RF signal, some pure carrier. You send it. It will be received by the spacecraft and it will send it back. And you observe the delay, whatever takes to come back, and that will, the speed of the light, and that delay will give you the range, but distance is not enough because it is a three object floating in six-dimensional space. So you need x, y, z, and velocity along all axes to exactly pinpoint where the object is. Now, if you can, now you have to angular orientation. If you have to find it out, you have to find out differential delay. If you observe the Doppler, that is the change in frequency, you can get the radial velocity. If you can observe the Doppler for longer time, you get the radial acceleration. And if you integrate the Doppler over time, then you can derive the same carrier. With the same carrier, you can do all these things. But let us do delay is very simple. You can just send some of the frequency and just see that phase of the return frequency and the phase difference between the received carrier and transmitted carrier will be giving you the delay. There may be phase ambiguity because it may undergo multiple 360-degree transition in the travel path. So you have to have multiple different frequency tones, and with that you can unambiguously derive the range using very simple formula. And if you have two ground stations on Earth receiving signal from the satellite, and they are quite wide apart, that is the distance between these two stations is b, it is maybe 4,000, 5,000 kilometers, that sort of distance I am talking about, or 6,000 kilometers. And if you can observe this delay in reaching the signal to this, means these two ground stations are time synchronized, means their times are very nicely synchronized using some radio stars or something like that, standard source. Now, these two ground stations receive the signal from the same satellite and observe the time delay to whatever they can record. So that time delay, that is delta tau into c, that is the light speed of the light, will give the difference in the range, that is the delta rho. Now from this delta rho, using this equation, you can get the angle of the spacecraft, that is the psi. So you just observe, you are just observing the signal from two ground stations, and from this calculation you can get the orientation of the spacecraft. And if you can observe the Doppler, that what I was talking, that Doppler will give you the radial velocity of the spacecraft. And if you integrate the Doppler, means you watch the Doppler over the time, that is, this is your velocity. So velocity, if you integrate over time to time interval, velocity into time is nothing but distance, and difference between two distances, that is t1 to t2, is nothing but range. So that will give how fast your object is moving. So using all these things, all these tricks, you can observe the spacecraft for a certain time. Say here you can see in the blue arc, I'm started observing the spacecraft from this point onwards, and I have using all these techniques I was observing, and I was just trying to find out the velocity, the position of the spacecraft. And I have another information, that azimuth and elevation angle of my ground station, and the range of the station satellite from the Doppler, and gravity model. Gravity model becomes very important when you are in space mission. So when you are close to Earth, only Earth's gravity you have to consider. But when you go a distance where gravity of Earth is very weak, and you are getting into the gravitational field of other objects like Moon or Mars or other things, so there you have to consider multiple gravity, and you have to generate their model, and you have to apply those corrections, and you'll be getting the extrapolated orbit of the spacecraft, and then you can predict where it is going, and accordingly you can apply the corrections. So when you are ready to go using this sort of experiment, this sort of calculations before cutting in the material, so then you have to go prepare the mission. So preparing the mission is it's a very iterative job, not a very difficult job. I should not say it's an iterative job, because launching every gram is very costly. So you have to keep the mass in check. And depending on your mission object, your mass get restricted. That is, you cannot launch whatever amount of mass you want. So you have to carry some fuels depending on the distance you like to travel. And the space available for putting into all these things are very limited. You can see the black outside boundary you have to put. This is the actually area that the rocket provides you. So you have to fit everything into that. And when it is launching, it is nothing. You cannot imagine how means how it shakes actually. You cannot imagine that one. So it has to undergo that sort of load, and it has to maintain its integrity. And one thing you have to understand that there is no scope of repair. Once it is launched, it has to work. So we have to take care of redundancy, means if one system fails, how other system to take care. And for deep space mission, manual intervention is not possible. For closed missions, you'll be able to watch the spacecraft and you can see what is happening, and you can be correct. But when you are talking of a very large distance like Mom and all, where the signal takes 15 minutes one-way travel, so half an hour back, after half an hour, only you can intervene. So by then your spacecraft will be dead if it is some critical. So your spacecraft should be intelligent enough to take some decisions and maintain its safety. And outside space environment is very harsh, like hard vacuum, and all these things will be coming into picture. Now, to understand how hard this environment is, you just imagine that you are burning something on Earth's surface. That is, the heat generated by heat released by this burning process is distributed in three modes: radiation, conduction, and convection. Moment you leave the Earth's atmosphere, your most favored mode of heat transfer, that is convection, is stopped, because there is no air to circulate or there is no liquid to circulate. So convection stops. So whatever energy, heat energy is generated here, it has to be, because if it is captured here only, then it will burn out. So if it has to radiate the energy, it has to be radiation and convection. You just imagine that you have a laptop or computer CPU. Just imagine a small thing that that fan of the CPU is not working. So after some time, it will heat up and it will stop functioning. And if you want to take it to even further, you just put your phone or something like that in a belcher and try to extract the air in between, and you just see how it operates. So it will burn out after some time. So in that case, so you have to start your redesigning the PCB. You have to analyze all the places of your PCB where the heat dissipation is more, this red color region, and accordingly you have to distribute the system at different places. So whatever in your phone you are seeing in hand size PCB, that will become 3 or 4 times of that one, because you have to distribute all the systems. Now to enhance that heat transfer with conductions, so thermal grease we call it, to reduce the friction, because when you place one object onto other, there will be in between gaps, and those gaps in general in air, in ground, it will be filled with air. But when you are outside, so there will not be nothing, so heat transfer will not take place. So you have to fill all these gaps with some material that is called thermal grease. And wherever energies are more, thermal energy generated is more, so there you have to increase the thickness of the metal block such that the heat capacity of that place is more, such that rise in the temperature is limited. And you have to apply proper fins and black anodizing to help the radiation process, that is to increase the emissivity of the material. And another nice thing, you just imagine a satellite in orbit, like here it is an International Space Station. So sun will be always one side. So one side will be always illuminated by sun, and that side will reach a temperature of 400 plus K. And other side, what it is there, it is nothing but cold sky. So it is 4K. So one side is 400K, other side is 4K. And your spacecraft is nothing but 2-3 meters or 5 meters at the most. So one side of a 5 meter distance is 400K, another side is 4K. So how to manage this environment? So for that, what it has to be done. You have to isolate the full spacecraft. It has to be wrapped with a MLI such that no heat exchange happens with uncontrolled heat exchange happens with the environment. And you have to put proper heater where it is getting cold. After analysis, you have to find it out. And where it is getting heated, there you have to make necessary arrangement for conduction or radiation of the heat. So this went with respect to the heat energy when you are living out of the Earth. Now, our magnetic field of Earth, it's like a mother's womb, I should say. It protects you from everything. What is that? No, this magnetic fields, it is nothing but magnetic line fields. Our Earth or any celestial object is continuously getting bombarded by high energy particle. That is one setup called galactic cosmic ray that is generated due to supernova explosion or whatever it is in a distant object. And sometimes radiations from the sun, that is when the magnetic field of the sun will get detached from the sun's surface. So it will come out with huge amount of mass, corona mass ejection. And those particles will be high energy particles will be ejected everywhere, and sometimes it will be reaching Earth's surface. And because of the Earth's magnetic field, those things will be channelized to your north and south poles, and we'll be seeing some lights there, different color of lights. So those are the very beautiful scene, but that's nothing but the channelization of this energy. But if you go beyond these things, so you have to, your spacecraft or your object will be bombarded with all these things. So what will happen? It will upset you. Means whenever some high energy particle hits somewhere, it will try to take out some electrons, or if it is very high, it will take out the proton from that particular place. It may damage. So if it is a logic device, that is a chip or something like this, it will upset the memory bit. Plus become minus, all these things, 0 become 1, 1 becomes 0. Then physical damage of the components. So like you have a BJT or something, so junctions are there. So that junctions is punctured by a high energy proton. And sometimes this energy charged particles will get accumulated on the surface of the dielectric materials, and it will discharge in a single shot, and that huge current will flow. And if you are in a manned mission and you are having such a high energy mission, and if you don't have proper protection, then that mission is gone actually. So you have to use proper component selection, radiation shielding, then correction logic, and properly design your mission such that all these things can be avoided. And of course, you have to have redundant systems. And once we call the reliability is it's a practice rather. Like as there is no scope of repair. Like if your car is not working, next day you call a mechanic or take this one to mechanic and you get it repaired. But there is nothing like this possible. So you have to take care of each and every component, and you have to arrange the component in such a way that if there is a weak component, like here, its reliability is only 0.6, all other are highly reliable components. So you don't put them in your series connections, because in series the connection of the total chain, the reliability of the total chain reduces because they simply multiply. If this is 0.9, this is 0.9, and this is 0.6, you can see overall reliability comes down below 50%. So there you have to adopt proper topology, like you have to use them in parallel connections such that the overall reliability, in spite of the weak component increases, you can see it becomes more and more reliable. So this sort of engineering approaches you have to take. Now, when you are in a mission, what do you carry? Means when you are going out for a trek or something like that, what do you carry? So that depends on your mission objectives. Completely depends on, dictated by the mission goal. So of course you'll like to carry a camera of appropriate nature. Appropriate nature means if you're going out to a scenic place, so you'll take a normal camera. But if you are sending a mission to a sun or something like that, those cameras are no use. So appropriate nature of, but you like to have some photographs, because that is the first impact that makes into our mind, the photographs. Now, for scientific mission standards, some of the standard things that I could mention is some spectroscopes that the students must be aware of spectroscopes. So every object emits some particular lines. So depending on the target object, you have to choose the spectroscope. And X-ray, gamma ray detector, because all the sources means like galaxies and all these things, they emit in this X-ray band, gamma ray, this frequency. Actually, if you see the our sky in this frequency band, it'll be maybe thousands or billions, millions times brighter than the normal whatever we see in naked eye. So you can have some radio sounding applications. You can carry radars, magnetic field measurements, and if you are going to land into that particular place, then you can carry some experiment for in situ analysis, like a laser spectrometer, laser for burning the soil there, and with the whatever gas comes out, with that you can analyze using spectrometer, and geophysical thermal measurements of the soil. And in the commercial applications, like we do geosatellite, geosynchronous satellite, and IRNSS or GPS, you can have a relay transponder, positioning, timing, accuracy, like cartographic measurement. These are the normal standard this one. But scientific missions, it is completely dictated by the imagination of the scientist and what they want to carry. And they can be comprises of all these things or even totally different this one. So this is the some typical payloads that a mission carry. You can see one terrain mapping camera. This is TMC. That means it is a 3D picture. It gives a 3D picture. That is your height of the place and depth of the place is very important. So we need a 3D camera. Here you can see this is a instrument to study the emissions emitted by the sun or the corona of the sun. And here we are interested in detecting the water. So we had a spectrograph in that particular emission band, OH hydroxyl and H2O emission band. So depending on that, we have to choose the detector or the filters for this particular frequency, emission band. Then there are main material that builds a rock, that is magnesium, aluminum, silica, all these things. They also have a particular frequency what they emit. So at that frequency, we have to have some just to analyze the chemical composition. So if you want to map this ice, it's synthetic aperture radar at S-band is very best choice. So depending on that. So if you want to analyze the neutral molecules available in this atmosphere, so you for that we have an experiment. So like this, you choose your experiments, and when you are landing there, so you can drill in that place, or you can use some of the sensor that can physically touch the soil, and they can measure the thermal conductivity, chemical compositions, whatever we can imagine on that. This one. Now, science mission and space mission, science objective and space missions are always interlinked. And till now, whatever I was telling, just what is the driving force behind the missions, driving equations or driving basic physics behind the mission. Now, sometimes missions also, space missions also drive the physics in the advanced level. That is to understand the basic how this universe was created. It's a continuing journey, questions. It is not yet answered definitely. And in that process, we send like Hubble telescope. It was launched in 1990. Then it was followed by Kepler. It was observing stars, and it has detected many habitable space, planets. Habitable planets means in our current consideration, we think a planet is habitable where water can stay in all his three forms, that is gaseous, liquid, as well as solid form. So those are the habitable range we call. So we have identified many habitable planets. So those are very important to answer the second question, are we alone in this universe? And then it is getting followed up by James Webb radio telescope. And as you know, if the signal is coming from the very close to the T0, that is the time of Big Bang, it will have more and more red shift. That is nothing but Doppler shift, but because it is ever expanding universe. So that red shift, the frequency will be shifting towards the red spectrum, infrared side. So this James Webb telescope has been designed to that infrared region, and it is expected to probe up to the level when initially the stars and galaxies are being formed up to this level. And Hubble used to probe up to this level, that is advanced levels of galaxy formation. And we are here already, galaxies and everything are formed, and we are observing from this distance. And the means oldest signal that we derive, that we receive from this one, is nothing but cosmic background radiation. That is CBM, that is a 4-degree Kelvin radiation. Whatever radio noise we get, that is not, that is the furthest signal we can get. Now, apart from these things, we have some, when you are floating in space, you are in micro-G, there is no gravity. So in that condition, you have some experiments, that is crystal growth, and some medical experiments that is being performed. And there is some thought of mining some of asteroid to extract the valuable material, and possible setting up of this one for further human exploration. Now, when you are getting into the manned mission, so it becomes really multidisciplinary. And here, failure is not an option. Here, specifically, failure is not an option. In your scientific mission, or whatever mission, you can fail, you'll be losing money. But here, though you can lose money, but you cannot lose a human life. So it becomes very critical. So it becomes a truly multidisciplinary in nature, not even interdisciplinary. So all streams of basic science, chemistry, physics, biology, mathematics, whatever you can imagine, those are involved. Engineering streams, whatever is there, I don't know, and some new engineering streams has to be set up for this study. System engineering, like life support system, mission design, medical science, psychology. Can you imagine that psychology plays a large role in this sort of mission? Food processing, ecosystem design, many more. And radiation from the solar flares and all these things that we told, when you are in a manned mission, this is one of the prime concerns. You cannot expose the humans or any living mission to such an radiations. So it will be catastrophic if you are exposing without any protection. And for a manned mission, you should have redundancy. I was talking that if one system fails, another will take over. So that is we call dual redundancy. But it is not enough. It have triple and quadruple level of redundancy, including design redundancy. Means one of the device is designed by me, another designed by somebody else, as the two designs are completely different. So that sort of philosophies we have to adapt. And you have to provide emergency ejection system, protection from radiation, and pressurized cabin and space suit. Those space suits are very heavy, 20-30 kgs, they have to wear it. Maintaining oxygen and carbon dioxide level, and to the required partial pressure. It is not that you put only oxygen, take out carbon dioxide. It's not like that. You have to maintain the partial pressure. And if some impurity gets into the air, you have to immediately remove them, supply of potable drinking water. And when people are confined in a small area, their moods will change like anything. So that proper training of the astronaut. And because you will not be undergoing a normal cycle of 12 hours day or 12 hours night, circular orbit will be always orbiting like ISS orbits around every 2 hours or even less. 90 minutes. So every 90 minutes, your day and night will change. So you'll not be, your sleeping vision will change, and it will be constantly noisy environment. It affects the human psychology. And for a manned mission, there is some physical effect. Actually, there's a lot of physical effect, because you'll be normally you'll be in 1G condition. When you are going to a floating platform, you'll be 0G condition. Then if you are going to moon, it is 1/6 of G, and if you are going to Mars, it is even, I think it is exactly half or something like that. So in coordination of your hand, eye, and your head, you are thinking that I can jump its ditch. But when you jump it, you'll be going further, or you may not be able to jump. You will be falling in between. So that sort of coordination will be required. And it is, you cannot pull something when you are in floating conditions. So those sort of adjustments you have to do. And because your body structure is not feeling the weight of your body, so your muscles or bones will not be growing, so they'll be decaying. Almost 1% of bone mass will be lost every month. And 1% is the general this one loss of bone for a person beyond 60 per year. So in this age, you can imagine this sort of, if you are in space for 6 months, you are losing 6% of, so you have to take adequate precautions for that. And whenever you are not there into the gravity, so your whatever fluid, that will not be coming down, it will be going upwards. So your pressure in the eyes will increase, and moment your blood flows out towards the brain will feel that there is enough blood, so it will stop producing the blood. So after some time it will be scarcity of blood. So, and because of the decay of the your bones, so there will be a lot of calcium will be going out, and that may lead to kidney stones, and many different problems may create. And you can see this is the right side on the astronauts are being recovered. Actually, this is shown as a glorified vision, but actually, if you leave that astronaut as such in this one, he or she cannot walk on her own and go come back to his place. So he has to be assisted because of all these conditions. So with that, I told you that I have in last couple of slides what I do, because I do a very small part of it. So you can imagine that we have to have a continuous communications with the spacecraft when you are in a mission. And for the only way to get connected to the spacecraft is through the RF link, radio frequency link. And for radio frequency link, there are three components: receiver, transmitters, and antennas. And receiver receives the signal, transmitter transmits, and they operate through the antennas. Antennas are like ears and eyes of the spacecraft. The signals get into through them. And when you are very close to Earth, then you need an antenna that covers a large part of the coverage area. So that time gain of the antenna should be small, and its coverage should be big. So we call it a low gain antenna. And moment you go little further, that coverage requirements comes down. So you can have a limited coverage antenna, and you can increase the gain of the antenna. And in some cases, you can increase the gain of the antenna even further, such that your powers are required power is less. Like in a Mars mission, sort of interplanetary mission, initially what I was explaining, that you initially revolve around the Earth for many days. So that time you will be having a lower gain antenna. As you go away and away, you need higher and higher gain antennas. So in my work, I designed some of these antennas that has been used in many space missions. So this is the job that I do, and my team does this full, we call it transponder, that is receiver, transmitter, antennas, all this put together, and we provide the full communication systems for a spacecraft to communicate with the ground station all the time. So you can imagine that understanding the basic physics always helps you. Being a student of physics, I also studied my physics from Belur Archimission. So it is always fascinating when you can analyze a situation that is non-nominal situation with the light of physics, physical concepts. that is very easy instead of getting into the engineering fast. And in the quest of learning the birth of universe or searching life in outer space, the space missions plays a great role. And space mission is truly an interdisciplinary nature. You cannot say that I am electrical engineer, I am a physicist, I am a biologist, I am this one, so I need not be part of this one. It's not true. You imagine any stream that is required for a mission of a big stature. And as I told, in a space mission, reliability and fault tolerant systems are the major requirement. Means you cannot. There will be failures. Some of the components will not last as you might have expected. So, so you have to have an alternate plan for that. And of course, it's a costly affair too. So nowadays, all space mission, that is mainly scientific mission, no nation is going alone. There, because science is developed for full humanity. So they are trying to collaborate with many nations and trying to have a bigger mission such that it can derive some meaningful science out of it. So with this, I think I conclude my, I stop sharing my thought. I hope I could convey what I wanted to, and it is useful to the audience. And I think I am also on time. So thank you very much once again, and for giving me this opportunity. And I also see Dr. Bhattacharya has joined this panel. So thank you very much, sir. I am also looking forward to listening to you. And maybe sometime I'll be joining through laptop, and then I'll be switching over to this one, because I'm eagerly, after seeing that topic, I was more fascinated in listening to that. It becomes that way. So with that, I hand over to Mrinal to take the proceedings forward. Thank you all. Thank you.
Thank you, Dr. Kumar, for your nice talk. Most of the physics that you explain is very tough to digest. Most of the people, like me also, as I mentioned earlier, that I had diverged to physics 12 years back. But some of the pictures, it's very common to us due to the YouTube, particularly from some videos of Dr. Sunita William. He used to upload in YouTube. But after overall, I believe this is a very informative session, and I can see many comments in the YouTube live chat box, and people really enjoy that comment. And if you have permission, I can request our faculties or other personnel who are available in the panel now, they may have some question.
Yeah, please.
Okay, may I ask our faculties, if you have any question, you can please raise your hand using the Zoom raise hand option, and I can go to you. Please check the raise hand option. While that time, I have one question that is actually I received from many people that is actually related to the Chandrayaan mission last year. Since you are the part of that mission also last year, what was the feeling or situation in your team when you missed just from this small distance? Can you please tell all of the viewers? Viewers actually wanted to know that.
Yeah, I think that is just exactly 1 year back. It was on 8th September.
And one more coincidence I want to tell you, not only your name, but also the time when you start to speak, that is around 2:43. That time the Chandrayaan 2 takes off. That time, the coincidence after coincidence with you.
Yeah. Thank you very much for watching this one. And that experience, probably, I hope that no other person should experience that one. But actually, we are totally blank at that time. Yeah. Totally blank, because we also was not able to feel what not to do. So all of a sudden, out of a lot of anxiety, all these things, just if somebody is was lot of pressure, and all of a sudden it was means you don't know it, like somebody jumped out of the rooftop and he's falling, and it's that sort of feeling. And of course it was not a very good feeling. So that's all I can share. But I hope nobody else go through that one. Though it is a part of our life, but it hope that nobody goes through that.
Exactly. I hope in coming future we may see many success mission conducted by ISRO. Well, I have one more question. Actually, it is came from one student. He is a class 12 student. He's asking that if you want to pursue his career in ISRO or any space agency, what will be your tips for that student? How he can prepare from his class 12?
As I told, the opportunities in space, this one is enormous. And probably if you confine to the Indian perspective, it is a little restricted. But if you are going to some other space agencies there, that's what I was telling, even starting from psychology to biology to bioscience, anything, any stream you name, even there's history, literatures, all these people are also required. The only thing I can tell the students, whatever you are doing, you love doing this, love doing that. Whatever physics, chemistry, or anything, you have to love that one. And there is always some process to enter into these things. So that is the secondary, I feel. So because once you get into that process, your love only will drive, your passion only will drive. That time your whatever you have learned, those things again you have to some of the things unlearn, and again you have to learn new things. So that passion only will drive. So study physics, chemistry, and maths, of course. Well, that is the main area, core area. But if you are in some other area also, there are scopes of getting into all these fields. So I'll suggest that try to love whatever you are learning.
Yeah. Okay, thank you. May I ask any other panel members if you have any question? So you can ask directly to the speaker. Dr. Pavi Banerjee, sir, do you have any question?
No, it's okay. It's fine.
Okay. Okay. And anybody else? I think it's fine that no other people have any other question. People are just trying to digest whatever you said. But personally, I feel that I definitely need to rewatch this again to properly digest the full information that whatever you gave. So if nobody has any other question, so I believe that we can conclude this first session now. And I want to thank you again, Dr. Kumar, for giving us time, and particularly he spent a lot of time to prepare his PPT, and he present here, and with his busy schedule, he manages time. And I want to request Dr. Kumar, please stay with us for the next session.
Yeah, sure. I'll be there.
Sure.
Because I am also, I totally looking forward to hear Professor Bhattacharya.
Sure. Okay, so now is also the time, already we have time to move to the next speaker. But before I move to the speaker, I want to share one interesting fact that, you know, in many times you experience that if you see some faces, that face are that much pleasant that one picture actually came to your mind that, yes, this person is very good. That exactly happened to me when I first time saw Dr. Bhattacharya's face in a social media. And then when I spoke to him for the first time, I realized that my feelings was not wrong. I was truly happy when I spoke to him. And I realized that he's really a nice person. Now, if I want to introduce that nice person, I think it's better if we have another nice person. That nice person is an ex-professor of Jhargram Raj College, and I was lucky that I got him as my teacher. And he's also equally very gentleman, known to everybody. So I want to request Dr. Pravir Banerjee, sir, please introduce our second speaker today.
Okay, thank you, Mrinal. Now, it is our great pleasure and honor that today we have here with us Dr. Sailajananda Bhattacharya, who is the former head physics department, Variable Energy Cyclotron Center, Calcutta, and also ex-Raja Ramanna fellow under DAE, that is Department of Atomic Energy, Government of India. Dr. Bhattacharya got his MSc degree in physics from University of Calcutta in the year 1976, and he obtained his PhD degree in the year 1989, that too from University of Calcutta. Now, after getting his MSc degree, Dr. Bhattacharya went to join BARC, that is Bhabha Atomic Research Center in Mumbai as scientist, where he was awarded Homi Bhabha Medal for acquiring first position in the orientation course in physics in the year 1979. And he was also awarded DAE Group Achievement Award as group leader in the year 2012. Now, he has guided 3 students for their PhD degree. And Dr. Bhattacharya, a renowned scientist of international repute, has published more than 100 papers in very reputed journals. Many of them are international journals. And his areas of interest include complex fragment emission in nuclear collisions, then nuclear reaction dynamics near Fermi energy domain, resonance particle spectroscopy, fusion fission dynamics in nuclear processes, and detectors and instrumentation. Now, Mrinal has said in the beginning that Dr. Bhattacharya is a very nice person, and let me tell you that I had the privilege of working with him as a postdoctoral fellow at VECC, Variable Energy Cyclotron Center, Kolkata, with Dr. Bhattacharya, and there also I had same sort of experience that he's a very nice person, other than being a very great scientist. With these words, I invite Dr. Bhattacharya to deliver his talk, and the title is Experiments in Science Triggering the Change. So, Dr. Bhattacharya, please.
Thank you. Can you hear me? Hello?
Yeah, we can hear you, sir. Please go on.
So, very good afternoon to everybody. And at the very outset, I must thank this Jhargram Raj College Physics Department and Jhargram Raj College Physics Alumni Association for giving me this opportunity to be introduced into this new virtual world of seminars. In fact, this is the first virtual seminar I am attending. So I had initially some hesitations, but anyway, Professor Pravir Banerjee, he insisted that I should give a talk. And then when I talked to Dr. Mrinal, then he nicely explained, because I had no experience of using Zoom, etc. earlier, because I was not in the virtual world as such. But anyway, after talking to Mrinal, he was a very nice person, so he very nicely explained. So I thought, okay, maybe it is possible for me that I can talk. So that's why I thought I will talk. And definitely, the previous speaker, you have heard a very nice lecture, very new and exciting information on the recent developments in science. And in my talk, however, I will do just the opposite. I will not give you any new information or recent development or anything. Rather, I will try to introspect. Introspect means how this physics has developed over the years and what is the logic, how logically it developed. So that is my aim. So it is basically a complementary to the previous talk, because definitely we need to know what are the developments going on at present, because there is exciting horizons in for the younger people, but at the same time, we should sometimes introspect also. We should also think, okay, let us go back and try to see how all these things develop step by step. This is also, I felt it is quite interesting. And this talk, therefore, will not be a very high level. It will be basically for undergraduate students. I thought that maybe I try to motivate undergraduate students for experimental science, which is very exciting, I feel, and that's why I thought maybe I try to do that. Okay, so with this, I start my talk. And okay, so what I want to talk in next maybe around 40 minutes or so is experiments in science triggering the change, means how the new experiments or novel experiments in science triggered the change of our concepts and our world of the field as a whole. Okay, so basically I'll not talk much on many topics. Just I will initially give some introduction. What is meant by experiments in science? Just a few general introduction, and then I'll try to illustrate this point. These experiments, how they really triggered the change. A few pioneering experience. But I shall caution you right at the beginning that there are many such pioneering experiments in many fields, many different fields. But I have just picked up very few, maybe 5 or 6 experiments here for discussion, because time is also short. And anyway, I am not qualified to talk about all such experiments in each and every field. So I talk about my field only. So let us talk. What is science? Science is basically, it is defined as a systematic enterprise that builds and organizes knowledge in the form of testable explanations. This is the important thing. Science is that branch of knowledge which always try to explain in terms of, it wants to get some testable explanation and predictions about the universe. And there are many branches of science we know of, say right from say earth science, social science, life science, physical science, formal science, etc., etc. However, I will restrict to my domain, that is physics, and I just try to pick up a few examples from physics to show how the experiments over the years, new experiments, I think novel experiments, has changed the landscape of physics and our knowledge. Okay, so this is how let me start how to pursue science now then. So we understand now that as science is defined, testable explanation means you have to test each and everything so that it can be qualified as good science. So you have to do experiments. So experiment is a basic part of science. And what is experiment? Experiment is a body of techniques for investigating phenomena based on empirical and measurable evidence for acquiring new or correcting previous knowledge. So that is what is experiment. Experiment means what happens? You do something, you collect some measurable evidence, means which is to be measured, which can be quantified. And with that, you try to just see whether whatever knowledge you had that is correct or not, or you need some correction, you put some correction over the previous knowledge. So this great circle of science in general is like this. So it rotates around these three basic, these are the spokes: hypothesis, experiment, observation. So what happens, you can start from anywhere. Suppose in earlier world, basically people started from observation. So from observation, what happens? You draw some inference about the things. And then from the inference, you come to land up in some theory, some hypothesis about this, why these inferences are there. And from these hypotheses, if they are good enough, they will lead to some prediction to whether this hypothesis is correct or not. Then according to this prediction, you design a new experiment. And this new experiment is basically testing this hypothesis. And so after this experiment, you see you get some result, that is observation, and this observation, if it is correct or not, on the basis of it, you draw a new inference. And during this new inference, if it is varying from the earlier inference, then you have to change your hypothesis. So this is how it rotates from hypothesis to experiment to observation, and from inference to prediction to testing. So this is how it is a never-ending cycle, and it goes on and on and on. And you see that definitely if any of the spokes are missing, then science does not exist, because then the experiment is missing, then there is no testing, so it is no more science. The science in this way we define. So therefore, experiments play key role in science, and we know, everybody knows about experiments. Many experiments are there, but definitely there are some major experiments which are really game changers. Game changers means they really change the perspective, whole perspective of science. Okay, so I just try to deal with a few such experiments, only a few, and maybe you can get. These are nothing new, because you all know that. I just try to just put a support for the experiment, why experiments should be done, because this is nothing new, but I just want to argue that good experiments lead to a change. Okay, so experiments now, before we go to the examples, let us discuss then experiment. How many types of the experiments are there? There are many types of experiments we know, but we can still classify them in two major types. One is curiosity-driven experiments. That means I just want to know why it is happening, or let us see if I do that, what happens. So this is the curiosity-driven experiment, which is basically leading to the basic research and leads to new discovery. Because unless there is curiosity, you don't go for, or you don't get a penchant for new discovery. So this is one of the main things, some curiosity-driven experiments. And then there is other class of experiment that is mission-oriented. Mission-oriented means what? Okay, as the previous speaker told, that we are trying to send some spacecraft to Moon or Mars or anywhere. And why we are doing that? We want to get information about the Moon or Mars or anything. And they are definitely new information. They will be of lot of help to us. So therefore, it is a mission. ISRO, it is a mission that, okay, let us send a spacecraft to Moon first. Then we will send to other places. So this type of research is called mission-oriented. They are called applied research, because directly you are not getting any basic information, but you are getting many new and important information, as well as in course of doing this, you also develop new technology. For example, say so many things that new technologies are developed because of this. Okay, I will not go into details, but okay. And then again, all these experiments are again we can divide into two major classifications. What is that? Say, for example, all these, even here, on both of them, one class is chance discovery. Chance discovery means what? Okay, you are trying to do something, but you end up with something we did not expect. And surprisingly, nearly 30 to 50% of all the recorded experiments, means major experiments or main experiments, fall in this category. Means they discovered something which they did not want or did not expect. Say, for example, say radioactivity, X-ray, superconductivity, fission. There are many. And in other fields also there are many. So they are called chance discoveries. Means you did not expect it. You wanted to do something else, you end up with something. And then another group is a group of experiment is planned experiment. Means, okay, you are doing something, you are planning to do something. Say, for example, for testing some hypothesis or for some applied research you are planning to do. So, for example, we know the bending of light. This is a testing of general theory of relativity. General theory of relativity predicted that light will be bending when it passes by the side of a very large gravitating object. But okay, it was something very novel, because light we always know it moves in straight line, but how it will bend and whether it is true. But this whole of general theory of relativity, it actually it lies on this definition, that whether if this is true, then immediately we can say that okay, basic tenets of general theory of relativity is true. So it is very, very important to know whether general theory of relativity is correct or not. That's why people put a lot of effort to test this bending of light. It is just during the, I think most probably during the end of First World War, at that time there was a solar eclipse, and in that solar eclipse they tried to locate the deflection of light ray from one star, distant star, which is just close to the sun. So, and ultimately it was really seen that okay, they saw some bending, and thus it proved that general relativity of these basic assumptions of general theory of relativity is correct. Then another great development is, for example, development of transistor. This is also a kind of a means. Okay, we knew that okay, semiconductors are there, but making compactification of three different types of semiconductor pieces, whether we can make some equivalent of a triode or not. That has enormous application. Now we know that it basically revolutionized the whole technology, because from semiconductor we get IC, etc., etc. But these are all basically planned experiments. So these are the two major categories in both of them. Okay, but one thing you always remember, that chance discoveries are also unexpected outcome of some planned experiment only. It is not that just you sit tight and think of something and you get some chance discovery. It is not true. Whenever there are some chance experiments, they are definitely trying to see something, some planned experiment. But ultimately, outcome was a chance discovery. So ultimately, so if you want to do some such a work, definitely you have to plan something. You have to plan a good experiment. And okay, if you are lucky enough, then that planned experiment may lead to something very unexpected result, and maybe you will start to fail. That is okay. But anyway, so these are the basic classes. And so we just try to elaborate all this with a few examples. Okay. I will take very few examples from this, maybe beginning of our quantitative knowledge almost. So shape of Earth. Shape of Earth, okay. In old days, what we knew? We knew that basically these Greek philosophers, they used to think that Earth is basically a kind of a flat disk floating in the ocean. And Chinese said it is a square disk. It is, anyway, it is a disk. It is a flat kind of thing. So it is the picture, this old picture, Thales kind of, they assume that this Earth was like this. It's a flat disk, where actually what happened, this land mass is floating in one big ocean, Mediterranean. At that time only that was known. Okay. However, with the advent of actually time, people found that there are some effects, there are some phenomena which could not be explained using this flat disk concept. One particular thing is this. So, lunar eclipse, if you see, always the shadow of Earth on the moon is curved. It is, how can it be? Because if it is a flat disk, it cannot be like that. So that cast a doubt that definitely there may be something wrong in it, because how can it be always? It cannot be like this. It is a curved thing, kind of that. This can only happen if it is a square or this spherical kind of object. And another experience, when actually at that time people started moving around in the sea, and then what we see, what they observed is that when the ship is moving towards the horizon further and further, ultimately what happens? First we see that lower part is not visible, and gradually it goes down as if, but it does not commensurate with this assumption of flat disk. Because if it is flat disk, then what happens? At the horizon it will suddenly dip down. But what happens? It is slowly, gradually coming down. That means as if there is a surface kind of thing. It is sloping, gradually sloping down the surface. So it also casts actually doubt on this picture of flat disk. And then finally, what happened? It was this Magellan's famous, everybody knows that this Magellan's famous circumnavigation, voyage, global navigation, he started from one place and came back ultimately to the same place. It cannot happen if it is, unless it is a spherical object. So therefore, this ultimately established that, okay, this Earth is not a flat disk, but it is a kind of a spheroidal shape. These are the very initial developments of knowledge. So, and then, okay, another initial development, but little bit late, recent actually I would say, is the solar system. What was our knowledge, old knowledge of solar system? This, again, these Greek philosophers, Ptolemy, Aristotle, etc., and even important this Christian church, they also said that Earth is at the center of the solar system and all others, moon, sun, everything, they are rotating around the Earth. So this picture was there, very much there for a very long time. And since chart supported it, nobody could raise any word about it. But then came actually Copernicus, who first postulated that maybe this is not true. Actually, solar system is heliocentric. Heliocentric means center, helios is sun. So sun-centric means it is not Earth-centric, but it is sun-centric. It is center is sun, and there are other actually planets and etc. etc. But when Kepler said so, nobody paid much attention except some maybe learned people or who wanted to think otherwise, because it is directly objecting, directly contradicting this chart's idea. But then what happens? Then came Galileo, and Galileo, what he did, he developed, at that time telescope was new in the market, and Galileo also developed one telescope. And with this telescope, he started looking at the sky, okay? And looking at the sky, he discovered so many things. Important is that he discovered several moons, 4 moons of Jupiter and phases of Venus. And from all these, he was confident that definitely it is actually this sun-centric system which can explain all this, but Earth-centric system cannot explain all this, particularly the phases of Venus, etc. cannot explain from a Earth-centric picture. So actually, Galileo, first observation of Galileo, this is the experiment, beauty of experiment, because he observed. So directly he is very confident. So he said that, okay, nothing doing, it is actually the heliocentric picture which is correct. But anyway, again, since he was a contradicting chart, Galileo, you know the story, means all this history, that Galileo had to suffer a lot, and ultimately he had to withdraw. To survive, he had to withdraw his statement that whatever he said is correct or not. Anyway, science actually goes, whatever is correct, ultimately it is correct. So maybe after some time, people agreed that, okay, it is only sun. Now we come to another great changeover in science. It is the rise and fall of ether and the introduction of theory of relativity. Okay, so what is the problem? Problem is that we know actually it is in the 18th century or early 19th century or so. At that time, we know, at that time we knew that light is a wave. Okay, it propagates as wave. But the problem is that at that time we used to know that, okay, wave is there, definitely fine, but all waves need some medium for propagation. Because say, for example, you know, wave on water, sound wave, etc., all need some medium. Without medium, how can it propagate? We know. But light comes from sun, and in between there is vacuum. So how can light propagate in vacuum? This was a big problem. If wave theory has to survive, then there has to be a medium. And if there is no medium, how it can be wave? How it can pass on as a wave? So to actually shape this wave theory of light, it was actually there was several models actually, and one of the most interesting model is that they conjectured that whole space is filled with some kind of material called luminiferous ether. Means this ether which basically transfers light only. And this, since it can transfer light, so it is a medium. So there is a medium, so there is no problem. Light can propagate to the medium. It's all right, fine, it is safe. But problem is otherwise. Problem is that, okay, if it is a kind of a fluid, whatever kind of, whether it is gas or something or anything, but strangely enough, if you see the property, velocity of light, if you know, and velocity of air, velocity of sound in air, if you know, and from there comparing, if you try to see what should be the property of this fluid, actually this is surprising. Tell you what happens, you find that it may be it has to be actually million times stronger than more rigid than steel in order to support this light frequency at such high velocity. So this is very peculiar. How can it happen? And at the same time, it is massless and it does not have any viscosity. Because if there is a viscosity, then what happens? All these planetary systems, they are moving in that, moving through that ether. And if there is a viscosity, there will be a drag. And if there is a drag, that means orbits will change, and ultimately orbits will. So ultimately orbits will change. So ultimately it will be a complete chaos. So therefore, but it does not happen because we know that these orbits are same throughout more or less the time immemorial, as we know. So therefore, there cannot be any viscosity. So how can there be a fluid, physical fluid, which is so strong, but at the same time it is massless and having no viscosity? This is really an anomaly. So people try to see how to save the grease, whether it is really there or not. Then came the famous Michelson-Morley experiment. He tried to see, okay, if this ether is there, then definitely, you know, all this famous experiment of Michelson and Morley, that light is divided and passed through two directions. One is along the direction of Earth's motion and along is perpendicular to the direction. So if really actually there is a drag because of this ether drag, then what happens? There will be a difference, path difference between these two light rays because the velocity will change. One is going, this one is going in, when it is going towards velocity, it will be c plus v. When it is coming back, it will be c minus v. So ultimately, okay, there will be a path difference between these two light rays, and ultimately it will lead to a shift in the spectrum. You know the interference spectrum. If you see, there will be a shift in the spectrum, and from that one can say exactly calculate how much is that drag. And this is the famous experiment, and it is a famous experiment which yielded null result. He found no shift. Therefore, this ether drag was completely not there. And even if it is there, it cannot be measurable. And as I told you right now at the very beginning, that once something is not measurable, in science, we do not bother about them. So therefore, it completely eradicated this postulate of ether, because we have no, scientist has no bother. Okay, philosophically you can keep on thinking all this, but you cannot, so far as you are scientist and it is not measurable, it has no deal with science. Okay, so it is gone, and then finally it is finally supplemented by this famous Einstein's theory of relativity, who based on this experiment proposed this postulates of relativity. Okay, that light is actually, velocity of light is constant and all this. This is basically a direct outcome of this type of experiment. Okay, so this is really a game changer in the field of science. We are from, say, classical Newtonian mechanics to relativistic mechanics domain, you come. Okay, so there is another game changer when we change from classical mechanics to quantum era, classical era to quantum era. In the case of microscopic world, what happened? This was again due to one pioneering experiment by Davison and Jhargram. What they did, okay? What they did is a very, very simple experiment. What they did, there was an electron gun. They just shoot some electron on a nickel target. And they wanted to see the scattered electron spectrum along different angular distribution of the scattered electron using some detector. Okay. So this is a simple experiment. What is the expectation? He was not bothered about quantum and all this. Though before that, already de Broglie actually propagated this idea that wave particle dualism, that any particle has got some wave. But he was not bothered. He wanted to do just simple classical experiment, and he wanted to measure that. And what he expected, that electrons are very small in size, microscopic in size, everybody knows. So therefore, if it falls on the surface of this nickel crystal, so even if not macroscopically it is a very plain surface, but actually microscopically to a very small size of particle, the surface there may be irregular, because it is a crystal. What happens is the atoms are arranged in some gaps, so therefore there may be some irregularity in between the gaps, and electron being very small in size, it will really see that it is not smooth surface. So therefore, the scattering, the electron scattering, instead of being a kind of a regular scattering, it will be a completely random or irregular scattering, completely diffuse reflection, not a regular reflection. So that was the expectation. And in actually, as I told you, that there are accidents sometimes happens, and accidents sometimes are good in experiments, but I do not say that, okay, you should always go for accident in experiments. But okay, in this case, one accident happened and it actually changed the whole dimension. What happened during the experiment? Some air leaked in, because it was a vacuum system, vacuum chamber. Air leaked in, and air leaked in means and it formed a oxide coating on nickel film. Okay. Now what happens? He wanted to study nickel surface, so therefore, to remove the nickel oxide film, the specimen was heated at high temperature. And what was the result? He did not know, but the result was that the polycrystalline nickel got converted into a large single crystal because of the heating. They all got aligned, and so polycrystalline nickel became a single crystal, aligned single crystal. And the outcome was phenomenal. What was the outcome? Outcome was that instead of a diffuse reflection, means which will be almost uniformly space distributed, he found a diffractive pattern with unexpected peaks. Very, very strange, because he did not expect that, unexpected peaks at some points. And this wave, when he calculated from this diffraction theory, you know that from this diffraction theory and electron velocity, you know, so when we apply de Broglie's theory, you find, and this crystal spacing we also know. So therefore, using this, we find that this lambda is of the order of from de Broglie theory. And from this scattering angle, this diffraction peak, if we extract this lambda value, it comes to almost very close. That means these electrons, they are not behaving as particle, but they are behaving like a wave. So this is the first direct proof of the wave particle dualism, which actually ultimately led to the breakthrough of modern science. That means it was first that, because before that we know that, okay, Einstein's this photon theory, etc., was about, they were all photons, but really particulate matter, whether they behave like a wave, this was the first demonstration, and it had very serious implications. It gave rise to all these future developments. Wave nature of particle was established, and it led to really a paradigm shift in our perception of micro world, because now we come to know that micro world is no more classical. It has become a quantum world now. Now we know that we completely complete change of ideas, and this is actually done by one of these main experiments. This is one of the pioneering experiments. Okay. And now, actually, finally, since I by training am a nuclear physicist, so let me go into some very novel venture in the nucleus. Means, how this nuclear physics also, they benefited from some novel experiments. And there are many, many novel experiments, but okay. So how, first of all, this we know, that how this journey into atomic nucleus went. Initially, we know that very old times, not even Dalton, even the Greeks, they actually conjectured this type of atom kind of thing, that okay, indivisible particle of matter which contains all this. But then it was Thomson who conjectured the atom to be consisting of positive and negative type of particles. And at that time, since electrons were only discovered, so Thomson assumed that atom is like that. It is actually uniformly charged sphere, positive charge sphere, in which electrons are put like a plum cake. Like in the plum cake, plums are put. So therefore, this positively charged sphere is the cake in which electrons are put as a plum. And then ultimately we know that from here, we know that this is the next is Rutherford who discovered that it is not like that. All this positively charged sphere, it is actually concentrated into a small, very small size at the center of the atom, that is called nucleus. And then came Bohr and all this. So now what I am going to talk about today in the next few slides is that how we know of the nucleus as we know today. Because from here to here, what do we know from nucleus now as on today? We know that now the nucleus is consisting of nucleons and means protons and neutrons. And if you go more deeply, the protons basically forms of quarks, neutrons also formed of quarks and all this. And then what we know of the properties? Properties also we know that, okay, binding energy is almost constant for nucleus. Means binding energy means if you want to remove one particle from the nucleus, then you have to spend this much of energy. It is kind of surface tension, as we know in classical. So this much energy you have to put to remove one particle. It is around 8 MeV like that. And we also know that nucleus is a kind of extended object having a nearly flat density distribution, which almost sharply falls up at the end. So this is a kind of a distribution is there. But the thing is how all these things are discovered, because they are not very small size. So how all these things are discovered? So I just try to spend a few slides on this only. Okay. So this journey started with the famous Rutherford experiment. Rutherford actually this same experiment it extended to discover one after another. Okay. One thing after another. Okay. So let me discuss. This is very interesting. The Rutherford experiment, what he wanted to measure. As I told you that chance discovery. So this is also a chance discovery, because you see, Rutherford did not want to discover actually this nucleus. What was the aim? Initially, his aim was to devise an alpha counter. Means alpha sources were available at that time, these radioactive sources. So he wanted to build one alpha counter. That means it will count every alpha particles passing through that. So he told his students, Geiger and Marsden, they are also famous scientists, you know, those who are reading nuclear physics. So Geiger and Marsden, they asked to design one air-filled chamber. So they designed one air-filled chamber. What happens, alpha particles, when it passes through air, it will ionize air. And if you apply some bias on these two electrodes, then you collect the charge. And from the amount of charge, you can find out what type of particle it is. Because if alpha particle is very heavy, so it will pass almost straight. Because in the Thomson ion, what happens? Atom is basically a kind of a what? It's like a positive charge particle is like a cloud. So through that cloud, actually, the ion passes, then it will not deviate. So it will pass through. So more or less, all alpha particles will pass through same distance. Therefore, pulse height of each should be same. Means you should get same type of pulse for every alpha particles. That was the idea. Because otherwise, how do you know whether it is alpha or something else? Every alpha should have same pulse height because they will have the same path length. But surprisingly, what they found is that this counter was not at all reliable. Why it is not reliable? Because they found that these pulsides of alphas are varying. Pulsides of alphas are varying. Okay. That is very strange. Why pulsides are varying? How path length is changing? They did not generate same number of ions, thus producing erratic result. That means all the alpha particles are not traversing the same path length. So they are as if someone is having this small path and then goes back. Someone is having it is going in a different direction. So pulsides are random. So if pulsides are random, then you cannot differentiate what is alpha or what is something else. So ultimately, it will be a total unreliable result. But the thing is that why it is? Because as far as your concept goes, that if it is a passing through a Thomson atom, it's basically a cloud of charged particles, positively charged particles. Alpha particle will simply pass through; it will not be deflected. Theory can very simply one can calculate that. So therefore, it is not possible. So therefore, Rutherford found out that the probable cause this can only happen if alphas were too strongly deflected by collisions with molecules of air. That means alphas really face a strong hurdle, very strong hurdle. It is like that. Suppose I have one ball in my hand and I am throwing it in the air. I never expect that ball will come back in my hand if it is a free space. But suddenly, suppose if I am blinded, I am blindfolded, I am throwing this ball, and suppose suddenly it comes back to my hand. What I will assume then? I will definitely assume that some very heavy obstacle is there in front from which it is reflecting back. So it is the same actually reasoning Rutherford put that alphas are coming back because they are coming back from they are facing a really heavy obstacle. It is almost similar or heavier than alpha particles. Then only it can come back, otherwise it cannot. So then the next question is, why alphas are deflected strongly? And therefore, you see the whole experiment, this motivation, now the orientation has changed. Started from this. And now what happens, as I said initially, this circle. So you started with one aim, experiment said something else. So you immediately change your idea and you said, now, why should it deflected? Why should it be deflected? So you study make a detailed study of alpha scattering and series of experiment, a detailed measurement with different foils you wanted to do. So only thing is that difference between Rutherford and common means and any other person is that he would have thought that the counter is wrong. This counter is unreliable, let us develop something else. That he had so much confidence in his result, then he thought that it cannot be wrong, measurement cannot be wrong. So something may be wrong with our physics concepts. That is what is the genius. Because similar result definitely many people have found at that time. Because everybody was experiencing similar. But they thought maybe okay, counter is behaving something physically, so forget about it. But Rutherford thought otherwise. He thought nothing doing. It is not. It is proper. Result is okay. Then why the result is deviating? That is why he started, and it was a game changer. So it is like this. Actually, this is, as I told earlier, it is basically shown in a mathematics. Just one projectile hitting a target. The result is that if, say, suppose the Thomson atom, as I said, Thomson atom, what happens? This is very, very small because charge particle is distributed in a sphere. Small particles, almost negligible charge. So what happens if it collides with each of them, any of them, it will not be deflected. So deflection is almost zero. Practically no momentum transfer, almost zero. On the other hand, if this is heavy, empty, this target or air molecule is heavier than alpha, then what happens? It will have a heavy impact, it will come back. The very large momentum transfer, so it will be coming back, it may come back. So something like this, second one may have happened, something like this may have happened rather than expected. So he thought, okay, let us see whether it is really so or not. So then actually he drive the second experiment. So this alpha particle, now it's same experiment, but now he is measured alpha particle at different angles. Okay. So deflection was he wanted to measure. So it is like this picture pictorially. So this deflection is very small if it is Thomson atom, and if it is something else, means very heavy thing at some point of time, at some place, then some of these alphas may get a large deflection. Okay, so from that we can infer that charged particles are not spread like a ball or like a. It is not a cake. Basically, it is focused at the center. All of the charged particles are focused at the center of the atom. And therefore, you have a heavy charged particle, and it is when actually these alpha particles are thrown at it, it will be bounced back. So this is what he did, actually, details of this experiment. But the thing is that you see the details, means how much time he had spent in this experiment. It is not that just like that you can do his experiment. Because at that time, the experiment was not easy. We did not have any automatic measurement or anything, any experiment to automatically measure. So what happened? He measured alpha particles with a telescope in which this eyepiece, he has put one zinc sulfide screen. Zinc sulfide is what? It is basically a scintillator. When alpha particle falls on it, it will give a scintillating signal, light. And what happens? You have to count, because at that time there was no electronics, nothing. You have to just keep on watching how many alpha particles are coming at each point of time. So you just, one comes, you just note it down in your notebook. So like that, maybe half an hour, 2 hours, 3 hours, you have to keep on counting one by one by one. So you just think of it, how tedious the experiment was. And why he actually still, and 1 in 8,000 alpha particles were backscattered. Just see, that means if you want to see really the backscattered alphas, 1 in 8,000 alpha particles backscattered. So just see the tremendous actually perseverance, tremendous amount of time he had to put just to see whether really you see any count at the backward angles. Because the sources were not strong like our beam. Nowadays we have very strong beam. You can do this experiment in maybe a matter of minutes or hours. But at that time it was a source, and alpha sources cannot be very strong. So it takes enormous time just to collect some data, because if in the front side you have 8,000 count, here you have 1 count. So one by one you have to collect. But still, why he pursued? Because it was in his own voice, in his own writing, it was quite the most incredible event that has happened to my life. It was almost as incredible as if you have fired a 15-inch shell at a piece of tissue paper and it came back and hit you. See, this is the kind of thing you are really looking. You are firing a shell and it is coming back, firing a shell on a tissue paper, and tissue paper reflects it back. It can never be possible, but that was what he found. And this actually ultimately led to this famous result that he came to know. He discovered this nucleus. He said that all charged particles are at the center. Okay, but actually, now what happens? What more we learn from there? Is the nucleus point-like or having some dimension? That is also because once we know that it is at the center, whether it is a point particle or it's having some dimension. Okay, whether other force scattering can say that? No, because it was done with a 5 MeV alpha particle. So with that 5 MeV, if you see, just simple calculate this, how much is the distance of closest approach? It is around 45 Fermi. So, whereas nuclear dimension, as we know now, is of the order of maybe 5 to 10 Fermi maximum. So therefore, it cannot reach even close to the surface of the nucleus, very far away. So therefore, you cannot say, you cannot come to really see the nucleus at all, very far away. It is from, we are looking at some, say maybe something from a very long distance. Okay. But then what he can conclude? You are seeing that even though it is reflected from 45 Fermi, this angular distribution, whatever he has found, it is purely 1 by sine theta 4. theta by 2, 4. That means it is pure Coulomb scattering. That means at that distance, the scattering is purely Coulomb. What it means? Nuclear, definitely if it reached the nucleus or touched the nucleus, there should have been deviation from this Coulomb, because nucleus would have done, actually reacted in some other way. But since it is not, at least it is the upper limit you can get. That nucleus definitely, or nuclear size is definitely smaller than that, and nuclear force also definitely is a short range, because it must be smaller than that. Because if nuclear force is there, then definitely at that distance, definitely you will not see the pure Coulomb. So even if you don't reach nucleus, you learn some more things. Okay. Still, this indicates that you should learn more things. But how can you learn more things? You can say simply that you increase energy. Just you increase energy. If you increase energy, you can become closer and closer and closer. So what happens? Higher the energy, you can go deeper and deeper and deeper. So, say for example, as long as your this, if you say in terms of de Broglie wavelength is much, much larger than the radius of the nucleus, then what happens? It cannot distinguish whether it is a point particle or a extended object. So therefore, if you increase energy of the beam, and if you increase the energy of the beam, then what happens? De Broglie wavelength reduces, because it is h by t. So momentum increases means wavelength decreases, and wavelength decreases means basically, if you see the beam, this is kind of a microscope, and resolving power of the microscope increases with the energy of the beam. So what happens when ultimately at very high, quite high energy, if the de Broglie wavelength is much less than the radius of the nucleus, and of the order of the radius of proton or nucleon, say, then what happens? You can really look into the structure of the nucleus. So that is also important, because here so far we do not know anything about the structure. We only say that, okay, Rutherford scattering says that there is a nucleus, which, and definitely whose dimension is small, and nuclear force is short range. That's all, and nothing else. But if you want to know more, we have to have higher energy. And then, for example, if you still have higher energy, then what happens if you go to radius lower than the proton radius? Then what happens? Then what you can explore? You can explore the structure of nucleon. That means whether nucleons have a structure or not. They may or may not have. Now we know that it has structure, but they may or may not have. Electrons, so far we don't know, because there is no structure, it is said, it is almost point. But so this is the things we can know if we can increase energy, and that, so therefore now we want to extend Rutherford scattering in higher energy domain from, say, maybe, and now what we think, we will change the projectile from alpha particle or light particle to electron for looking into the nucleus. Why? Because two advantages. One is that electron is not a nucleon, means it does not interact via strong interaction. So therefore what happens? Electron, when it interacts with the nucleus, it will interact only with electromagnetic wave, okay, and which is very well known. That is one thing. And moreover, we also know that electrons does not have its own structure. So what happens when you probe something with electron? You know that electron does not have structure. So whatever information you get, it is belonging to the other part. But if electron did have some structure, then what happens? These two structure informations will get mixed up. Okay. So therefore, higher energy, rather for type experiment at higher energies, people wanted to see that they want to carry out with electron. And for electron, okay, it is also same Rutherford scattering similar, but only thing is that it is called Mott scattering. Mott scattering is the modification of Rutherford scattering to take into account the spin orbit, the spin coupling effect of electron. Electron, if you spin, you can consider then some coupling term, but that is not important for us. What is important for us is that, okay, using electron, we do the same Rutherford type scattering, and we should see some distribution. Okay, but what will be interesting? Interesting will be that if there is a deviation from Mott scattering, because So Mott scattering is also for whatever. Pure Mott scattering means you are assuming the charge center to be a point-like particle. So therefore, if it is not a point-like particle, then it will not be a pure Mott-like scattering. Because say for example, Rutherford scattering when we did, it was very low energy. Therefore, to these alphas, low energy alphas, nucleus appeared to be a kind of a point particle, and therefore you saw pure Rutherford scattering. That means Coulomb scattering. But if electron energy is very high, then actually what happens? It may not. It will go very close to the nucleus. Maybe it will enter into the nucleus. Therefore, it will not be a pure electron proton or electron particle nucleus Coulomb scattering. There will be deviation because of the finite size of the nucleus. And that is what was exactly seen. That if this is the Mott scattering for point, assuming point nucleus, then scattering cross section found to be like this. So from this, how do we extract the information about the nucleus? Okay, it is done normally this way. These are some technicalities, but what I would like to say is just that. So suppose experimentally you measure some angular distribution. Angular distribution means at each angle how many particles, electrons you detect. That is the angular distribution. Okay, so this angular distribution we measure. Now this Mott scattering we know that how to calculate, and then we assume that if there is something, it is a finite shape will distort this by some factor which is fq square. I would say q is momentum transfer, or it is, I would rather say it is depending on basically the theta angle of the scattering angle, because momentum actually transfer is basically depending on the angle. Okay, so it is basically a theta dependent part. So this fq is basically called a structure factor, form factor of the nucleus. So, and it is basically Fourier transform of the density function of the nucleus. So basically it is Fourier. So if you know fq, then you can calculate, you can get in for estimate this rho r. Rho r means nuclear density distribution. So typically how it will look like. So for example, if rho r, if we assume a point-like particle means rho r will be like this, a delta function like this, and then fq will be a flat thing. It will not change. So therefore, in that case, Coulomb and Mott will be same. Experiment and Mott will be same. But if you have different type of distribution, with rho r, you do not know what is rho r, how nuclear density function looks like. So if you can calculate with different type of densities, and different type of density functions, we see fq values are different type of shapes. So therefore, from the shape of the scattering, this angular distribution, you can extract both the radius as well as the structure of the nucleus. And that is what was done. This is a typical scattering result. And from all these results, ultimately now we know that nuclear charge distribution is like this. It is more or less flat at the center, almost flat, and suddenly it comes to a surface and it falls down. It is typically this type of distribution. It is called a typically wood section kind of distribution. It's a flat top and then it falls suddenly at the edge. So this is a typical distribution which actually is valid for all results. Okay. Okay. Similarly, one can do this experiment. So this will give you charge distribution. So, but mass distribution, you cannot directly say from this. So therefore, from that, you can use some, using some elastic particle source projects, particle scattering, proton or something. And from particles, this is a rather, I would say, some kind of model dependent thing. You use some optical model type of analysis and then you find out the mass distribution. This gives you directly, electron scattering gives you charge distribution. This gives you mass distribution. But they are more or less same type, flat top, and then falls at the end. Okay. So this is typically we know using electron scattering. Okay. And then actually, as I said, if I still increase the energy, alpha energy, electron energy, what will happen? Here, what will happen is that again, it will go into the proton, and if proton has got some structure, it will interact with the structure and it will get result. So suppose proton has got some structure, then again what happens previously, as we said, electron goes in, and ultimately the result is that you have some inelastic scattering, and from the deviations you can try to guess what is the structure. The same philosophy is same everywhere, but only thing is that energy is high. So people did the same thing. They bombarded very high energy electron so that it goes into, looks into the particle, proton or neutron, and what is the result? And this result is that this is the result. Actually, they really found that proton has got substructure called quark. And the peculiar property of quark, what they found, that this electron scattering, this deeply inelastic scattering, it is similar to kind of free electron quark scattering. As if the quarks in these protons, quark neutrons, they are free. And if they are free, then it will be a pure elastic scattering of electron and proton, electron and quark. So, but we did not expect that. We expected what? Proton is a strongly bound particle. So all these, because see, within a nucleus, all these nucleons, they are very strongly bound. So similarly, proton is also a substructure. Then within the proton, all these other subatomic, subnucleonic, those are called partons. Initially, they were called partons. They also should be very strongly bound, but it is rather opposite. Found that it is not strongly bound. Rather, from this scattering, which is almost elastic scattering like thing, they found that it is not strongly bound. Rather, they are elastically scattered. That means within the proton, these quarks are almost behaving like free particles. So this is another puzzle. We again discover the substructure of parton through again the same kind of scattering, same kind of Rutherford, maybe modification of Rutherford type of experiment, that you look at the scattering, you look at the deviation, and from the deviation you try to extract the result. So this is a great idea. What I wanted to say, that gate experiments are like that. That when you put a gate experiment, you can always have a lot of extension. You extend the ideas to different domains, and it will be useful definitely. Rutherford idea, this Rutherford scattering idea is used. You see, starting from the discovery of nucleus, same idea was used for discovery of the, actually not discovery, I say from the, for elaborating the structure of the nucleus, that is how the charge distribution looks like, and then finally what is the substructure of protons, etc. What are the nature? Because this led to actually the ultimately revolutionize the theory of strong interaction, what is called quantum chromodynamics. This almost three particles, three protons and three quarks within the actually proton or neutron, they are actually explained by they actually led to the theory of what, that is chromodynamics. Ultimately, this is the theory of now what is said. This is the theory of strongly interacting particles. So therefore, we see now we come to almost end that Rutherford scattering, we see a lot of new things at different energies, and it gives you some new information. When projectile energy is very small, pure Rutherford scattering, it leads to discovery of nucleus. Simple discovery of nucleus. But now what happens? Same scattering, if you go in at higher energy, then what happens? It leads to structure of nucleus. Which here you are only discovering it, but then you are improving on this discovery. You are saying that okay, it is extended object, it has got a structure, it has got a charge distribution, it looks like this, and sign of that. And then if you go to further higher energy, you find that really protons, etc., are also having some structure, and actually it leads to the latest this quark theory of matter, that is the quantum chromodynamics. So therefore, that's what I would like to say, that Rutherford scattering is really one of the path-breaking experimental technique in nuclear physics, which like the other experiments I showed earlier in different areas, Rutherford scattering really revolutionized the whole of nuclear physics. It just changed the whole actually picture of nuclear physics at different stages with new energies, new beams, and ultimately you see new results. And ultimately all new results. And what we know, complete change in picture from Thomson scattering, from Thomson picture to this quark picture, all are because of this single one idea, that is the Rutherford type scattering. Okay. So ultimately, what do we learn? So that is what is the importance. What do we learn from all this? So definitely, what we learn is that actually how to do that, you should have a good motivation. Unless, because Rutherford scattering initially, very initially, most of the people will say that, okay, forget, nothing doing. It is a wrong thing because whatever result you have got, it is because the detector is bad, so forget it. But motivation should be strong. You should be, if you are sure that, okay, your detector is right, then definitely you have to, you stick to your goal and keep on. And then you change your goal. That is also important. That is another thing. Initially, you tried to measure alpha, but now as soon as you found that, okay, it is showing something else, you change the baseline. You say that now, okay, I will measure angular distribution to see really how the scattering looks like. It will lead to new discovery. This is very important. And then you should have some estimate definitely. Otherwise, what happens, whether it is how much time it will take. Because, for example, Rutherford scattering, as you said, as I said, that in the backward angles, 1 in 8,000 particles you will see. And see how much enormous time one has to spend. Unless you are not convinced, you will feel forget, let us not do it. Because at that time, maybe hours we have to see just to see one count. And you can only do that only if you are convinced that definitely some particle will come at some time. So this estimation, proper estimation is very important. And then definitely interpretation is also very, very important. Because you see the result, if you cannot interpret the result, okay, it may lead to a disaster because somebody else may later on understand, may properly interpret, and they may get the all credit. There are several examples of this type of thing, that experiments were done but could not be interpreted properly, and which led to actually misfortune. In India also, actually, maybe some people know of some experiment here in Calcutta, that one person, actually, she was one lady basically, she first measured this positron. Okay, there are two, one is this fission also was measured, and positron was, there are two measurements. So positron was measured from cosmic shower, but ultimately what happened, his boss told no, nothing doing, it is actually a wrong result, because basically you are doing in cloud chamber, and in cloud chamber lots of such photographs are there, and sometimes it is very difficult to see that, okay, it is correct or not. So it was just junked. They said that nothing doing, forget it. And then ultimately what happened, a few years back, the same experiment was done in UK. And what this fellow did, he was convinced that something new is coming. So what is it? Only he put some lead plate on the top of this detector with cloud chamber, and then whatever all these junks went away, but still this other one is still there. So therefore now it is clean, and he clearly demonstrated that it is something else. It is a new kind of particle positron. He got Nobel Prize. So then, so what happened? You have just missed this thing just by chance. So it happens. That proper interpretation is very important. And then once you set your goal, you must do proper follow-up. Because if you feel that, okay, there is something new you can get, but you do not follow it up, then again also you miss the bus because you cannot get it. And definitely, to do all this good experiment, definitely, my idea is that actually to tell you that if you want to do good experiment, you should think of, then you should have the following qualities. You have to have positive thinking. That means do not lose heart in failures. You should be open-minded, because you should be interpret data without bias. Because what happens if you are thinking that, okay, whatever you have done is correct and it cannot be modified, then ultimately you may miss some new result. And definitely there is no question that you have to be hardworking, and already you have to be aware what are the current developments in other places, because you may be doing the same thing which other people have already finished. That there is no. Okay, so this is all what I'm trying to say, just to try to say how good experiments actually change the shape of the physics or maybe science. Okay, thank you.
Okay, thank you very much, Dr. Bhattacharya, for this nice motivational talk aimed at very basic level, particularly for the students. By citing examples of some well-known experiments, you have amply demonstrated the role of experiments in the development of science, and this in turn leads to development of new technology and brings out the ultimate truth in nature. Now, it is my pleasant task to ask for some questions, particularly from the students. Please, some questions, please. Any question, please?
Well, I have one question that I took from the YouTube chat box. Somebody is asking that, is there any conceptual relation between the gravitational wave theory that recently came with the very much old ether theory?
Ether theory is completely, nobody talks of it. It is only of historical consequence. And gravitational wave is a purely fallout of Einstein's theory. Okay. Yeah. So I think that is, because ether theory anyway, nowadays nobody talks of, but only thing is that I just mentioned it, how science developed. Because it is just historical significance, nothing else. Yes.
Well, another question that very general question even, that how to teach physics in a manner interesting and simple way to the student that student can have interest on the field.
Okay, so maybe Pravir can tell it better because, and you may also tell it better because you are directly interacting with many students. But what I feel is that why I wanted to talk in this way, because what I feel is that unless science, if you miss, experiment is a main part of science. Because what I wanted to show in this talk is that major results or major ideas came from new and path-breaking experiments. So unless you really do not know the perspective of experiments, how it led to the development of science, then actually what happens, you will feel you will not feel interested. So sometimes what happens, this coupling is very important because you need to know the background. So my idea is that just to give you the background, because whatever I said is nothing new. What is the background? So this background has to be known. And more or less, good experiments, actually they should be exposed to more good experiments during their curriculum. Because that is, okay, maybe there are other problems, infrastructure problems in colleges most of the times, which actually stops from, but still, okay, I think maybe people, there should be more connection between these good laboratories and actually these colleges, so that they can have regular visits, so that they can come together and regularly have interaction to know. Say, for example, the previous talk, very interesting talk, what is going on in this domain, means our domain. So, but what happens, you regularly, so there are many other fields, actually people are working like that. So what happens, suppose people, they should regularly visit different laboratories, they should be allowed to interact with the working scientists to know what are the forward areas or frontier areas of science, because that is the area where more exciting things is going on. No, because whatever you are reading in books, they are important because they are basically a logical development of mind, is for that you need it. But at the same time, you should also have an idea what is the horizon and what is the exciting activities going on in the horizon. So for that, actually more interaction is needed. Unless that interaction is needed, actually you may feel little bit that as if, okay, whatever you are doing, maybe that is all and all this. So this fuzzy area, diffuse border is also to be known.
Yeah. Actually, why I asked this question, that I found that gradually the interest in physics from the student community is gradually decreasing, not only in our country, but I read one article in American Institute of Physics. They started in around 2004 that they also found that in America that time also the students gradually lose their interest in physics. So how we can develop the interest in the student, particularly in the place like in Jhargram, where we have very less infrastructure available, resources are very less, and money is definitely a factor. So what a teacher from that kind of institution can do something that can create extra interest on the students, then they can able to read physics by themselves from their heart. Not that was actually my query.
Yeah, that is what I was telling. I tried to say that, for example, means people will be interested if younger people particularly will be interested to join, do the experiment, do science, if they see that really some exciting work is going on somewhere.
Yeah.
Because most of the time we are reading from the books, but we do not see. Say, for example, how many people, we have so many accelerators in India now also, but how many people have visited the accelerator laboratories in India? Because you are reading and all these alpha scattering, these, that, you are doing all this reaction, nuclear reaction, but how it is done, what is the scale of experiment, how it is done, that if you do not know, if you see, then you will have some interest that, okay, it is a big thing. Say, for example, this kind of previous talk you said, it's a huge thing, huge activity. But once visit there, you will really feel that, okay, it is a challenging activity one can join. Similarly, for other activities, other areas of physics also. That is the main problem, that means regular interaction between the laboratories where actually work is being done on the frontier areas of physics and say students. That is very much needed. Say, for example, if you go to CERN, they regularly organize the summer school, these, that, where all students from Europe come. Even it is not only BSc, they will actually invite students from schools level also. Because interest has to be developed from that level. From school level, people, they come, they do some simple experiment, they set up for them, they do with their own hand. So this type of thing, why they do? Again, it is to pick them young kind of attitude. Because unless you develop this interest right at a very initial stage, then actually you cannot just develop it at a very later stage. Another thing is that definitely another thing is economic factor is there. Because now everybody, because livelihood is definitely another factor. So therefore, if you see that, okay, livelihood, if you read physics, your livelihood is not guaranteed. So therefore, you try to see. That is definitely a factor. And that is why actually it is not in India. Throughout the world now, basically in basic science, actually funding is becoming less, and therefore interest is also becoming less. But it does not mean that people are not working. Really, a lot of people are still working. But definitely interest has shifted. And whenever there is a fund cut, we will find that fund cut first comes from the basic science.
So I believe that the message from you is to the teachers that they should arrange some lab visit from the school level. Then maybe students will acquire some knowledge and some interest will develop automatically on them, right?
No, that is true. Hello?
Yes. Yes.
Yeah, that is true. At the same time, what I would say, that it is not one-way traffic. Actually, laboratories also should on their own develop make some program and try to bring people to the laboratory. It is not that only actually say from the students, say teachers should actually write to university, laboratories and so to fund visit and all this. Actually, laboratories also should have some dedicated time fixed for student interaction. So they should have some fixed sun, and on all big laboratories in other places they have like that.
Yeah, I think, Dr. Bhattacharya, I think VCC organizes one-day program that is on the National Science Day for students from schools, colleges.
Yeah,
they could go there and just visit and see things.
Yeah, you are right.
Can have a first-hand experience.
I'm saying that one day may not be enough. Actually, you should have regular such programs. Maybe every 3 months or every 2 months, or we should have 2-3 days or 2-3 weeks. We have to have some where people can come and interact like that. It is only one day. Definitely, I know that it is there. One day may not be enough. That's what I'm saying. Maybe during summer vacation. one can spend some time. Summer vacation or maybe winter vacation. So this is, I don't know what happens if everything is gone. Or
I have a very small question.
just a
I have
minute.
a small question. Hello.
What is that? Yes, I can hear, but I cannot see you.
Uh, okay, I have a small question.
Yes.
How was the superconductivity accidentally discovered? Can you please tell us?
How much?
Hello,
Uh-huh.
am I audible?
Yeah, yes. Yes. You tell me. Yes, hello. Hello.
Hello.
Yes.
Yes, sir. Please repeat your question, sir. PV sir, please repeat your question.
Yeah, how was this superconductivity accidentally discovered?
Accidentally means what happens, you know, that this Kemmerling owns, he wanted to actually cool down the some conductor and tried to see how this conductivity property is changing. So at some point he suddenly saw that actually there is it shoot up. Actually, suddenly it becomes superconductor. It is like that most probably, as far as I remember. It was like this was basically something he did not expect.
Okay, are there any further questions? Are there any more questions? If there is none, then it is my turn to hand the mic over to Mrinal.
Okay,
Mrinal.
thank you, sir, so much for conducting this session. And I want to thank you again, Dr. Bhattacharya, for his time, because I know he spent huge time to prepare this PPT, and I know how difficult it is to make a PPT presentation for any seminar. And
it is my pleasure actually. And actually, what happens, I should rather thank you all because it is my introduction to this virtual seminar world, because this is my first virtual seminar I attended.
I hope after this, sir, you will get many more opportunities, and this is the fact now in coming days that
that
virtual
new normal.
seminars is the reality now.
Yes. Okay.
So thank you, sir, so much. Please stay with us. I want to move to the closing session of this webinar, and let me ask Dr. Dept Roy again for his closing remarks. Dr. Roy, please. How do you feel about the whole session today?
Actually, I have today listened a lot of knowledge and gain a lot of knowledge from the deliberation of Dr. Chandrakanta Kumar as well as Professor Sailajananda Bhattacharya. And with their lucid deliberation, I enrich my knowledge. Actually, basically, I have a background of biology. Basically, I am a student of zoology. I have learned a lot of human evolution, but I have a little experience about the scientific discovery, invention like that. And just like a schoolboy, I am listening Professor Sailajananda Bhattacharya. I once again express my heartfelt gratitude and my pranam to Sailajananda Bhattacharya. And from this platform, I once again invite you, sir, and also Dr. Chandrakanta Kumar to visit our college. And after this COVID situation, we hope in near future, Jhargram Raj College Physics Alumni Association organize such interactive session, and with their presence, and we also enrich our knowledge in near future. We hope in near future we overcome the COVID situation, and thanks to all for organizing such a good seminar. Thank you, sir.
Okay, thank you for hosting this very nice seminar series. Okay, it's a commendable job. Okay, thank you.
Thank you, sir. Thank you, both of you, Dr. Roy and Dr. Bhattacharya, for your comments. Now, I believe it's time for the joint convener of this webinar series, Dr. Shubhasree Pradhan. Shubhasree, can I ask you to express the vote of thanks, please?
Yeah. Thank you, Mrinalda. Namaskar and very good afternoon to everyone. My honorable dignitaries, respected principal sir, dear colleagues and dear participants. On behalf of the Jhargram Raj College Physics Alumni Association and the Department of Physics JRC, I take immense pleasure to propose vote of thanks for putting this webinar together through your active participation. First of all, I express my sincere gratitude towards Dr. Kumar for his lucid talk and his time and contribution. He enlightened us with on space mission, starting from very basic or very fundamental classical mechanics. We also learned space mission or Chandrayaan has become an interdisciplinary topic. So then I further extend my hearty thanks to Dr. Bhattacharya, who enriched us with his profound knowledge on nuclear physics and its connection with basic experimental physics. So in physics, we know that sometimes theory comes first and sometimes experiments. But being a theoretical physicist, I must say, whatever is the theory or hypothesis or numerical evidence, the final thing or the end has to be with a valid experiment. I mean, we should have a very valid experiment to prove the theory or the hypothesis. So we learned a lot of basic things from Professor Sailajananda Bhattacharya. Thank you, sir. Thank you very much. And I would also like to thank our principal, sir, Dr. Devnaran, sir, for being with us in all the webinars and all the conferences that we arranged together. And he has remained to be always supportive and always with us. Thank you very much, sir, for being with us. And then I'd like to thank, especially thank, heartfelt thanks to Dr. Hota, Dr. Mrinal Kanti Hota. He put a lot of efforts, enormous amount of time from his work schedule, starting from making the poster, organizing things for smooth conduction of the program. But he is not mentioning his name anywhere, but he is everywhere for making this program a successful one. Along with this, I thank all the members of Jhargram Raj College Physics Alumni Association for their active participation and encouragement, their suggestion and all. And also I would like to thank dear students and participants for being engaged throughout the time and asking questions. And I would also like to update you all that we have many such webinars in the pipeline. So we will keep you updated and hope to see you again like this, your engagement, your involvement in the upcoming webinars. So thank you all once again. Thank you very much and have a good evening. So stay well. Thank you. Thank you, sir.
Thank you, Dr. Pradhan, for your vote of thanks. But one small correction I have: the posters that you saw so far, that is not from created by me. That is from Sandipan. He is the artist from in our group. Whatever he draw like this, it become a poster. Okay, so and my job is to do the final touch and poster in different places. Anyway, with this, I believe that we have a very wonderful session today, and we are able to learn many things from both of our speakers. And I believe in future, if we will have a opportunity, then we may organize a physical event inside our college. And as Dr. Roy already mentioned that we may definitely invite them if the schedule match with them. Then I hope we will get them physically. So with these remarks, I want to end this live session. And I also want to announce from this that we'll have few more webinars coming soon. Particularly next week, we will have a webinar, particularly for the physics honors student. That is a career guidance type program, what they can do in higher education or what is the job sectors from them. This webinar will be presented by our two ex-HODs, Professor Ranjan Chaki and Professor Shantanu Dhar. We will advertise the date and time very soon. With these remarks, I once again thank you all to stay with us. Be